In 1924, a German psychiatrist called Hans Berger put electrodes on a human scalp and recorded the first EEG. He was not, at that point, doing entirely respectable science. Years earlier, he had fallen off a horse and nearly been killed, and at the same moment, his sister, kilometers away, had been overwhelmed by a feeling that something terrible had happened to him. Berger spent a good part of his career trying to find the physical energy that carried the message. He never found it. What he found instead was a rhythm, around 10 cycles a second, strongest when someone shut their eyes and did nothing. He called it alpha wave, and it is still one of the most studied signals in neuroscience. Now, here is the thing. I actually want you to, take from that story. He wrote his recordings on paper and measured them with a ruler. You have a laptop, and about 8 to 10 minutes you're going to generate a signal like this at 500 samples a second and measure it in a fraction of a second. That is what today is about. Why lists stop working? Personally, I love lists and I love the concept of list comprehension. But the story does not end there. Quick reality check on scale. One EEG channel at 500 samples a second gives you 30,000 numbers a minute. That's one channel. Normal research setup has 64 of them, running for maybe 40 minutes. So you are into tens of millions of numbers and you want simple things. The average, the standard deviation, and the mean. Everything multiplied by a calibration factor. Python lists can hold that, they will just be miserable about it. Let's race them, same job twice. Take a million numbers, double all of them, once with a list and a loop, right here, and once with a NumPy array. Lists 80.4 milliseconds and arrays 2.9 milliseconds. That gap is not a small optimization. That is the difference between an analysis you run whenever you feel like it and one you start before lunch and hope for it to end. The reason is that a Python list is a box of pointers to separate objects scattered around memory, and looping over it means Python checks the type of every single element every single time. A NumPy array is one solid block of numbers of one type, and the actual arithmetic happens in compiled C code underneath. And look at what the fast version looks like. No loop, no brackets, just array times 2. That style has a name. It's called vectorization, and it is the single most important habit in scientific Python. If you find yourself writing a loop over a signal and stop and ask whether NumPy already has the operation. Making arrays. 4 ways in and you will use all 4. You can build one from a list, like you already have a list, want to vectorize it, which is what you do when the data arrives from somewhere else. Zeros, like np.zeros, gives you an empty container of known size for when you are about to fill something in. Remember, like back then when we were creating an empty list and trying to append stuff into it? Arange is like an arrange with a step size. Start, stop, and step. And int and linspace gives you a fixed number of evenly spaced values between 2 endpoints. Arange and linspace look almost identical, the same, but they are not. So let me be clear about the difference. Arange takes a step and leaves out the endpoint. Linspace takes a count and includes it. I'm sorry, I should be pointing into those two. time axis, you almost always want a range. Because what you know about your recording is the sampling interval. Sampled every 2 milliseconds. For example, you do not usually know or care that there were exactly 1001 samples. The last line here prints the shape and dtype. Dtype stands for data type. What kind of numbers are inside? Both of those will save you at some point when something is behaving strangely and you want to find out what. Okay. Now the important part of today. This function is going to follow us all the way to the session 9. Every session from here builds on it, so you will see it again and recognize it. It does two things. It makes a sine wave at 10 Hz, which puts it right in Berger's alpha range. Then it adds random noise on top. And I want to be completely straight with you about this. It's a toy, it's not recording of anything, and it is not a simulation of a neuron in any meaningful sense. It's a sine wave with noise sprinkled on it, and I'm using it on purpose for one reason. I know the right answer to it. When we filter this in session 8, I can check whether the filter recovered the thing I put in or not. You cannot do that on real data, because the real data, you will never know what was truly there. Learn your methods on data where you know the answer, then point them at the data where you do not. This is the logic I've been following in every learning session I've been having with myself. So let's run this cell as well. Okay, let's see. 2 seconds of signal, 500 samples. The sample rate here. 500 samples a second, so 1,000 numbers. Let's get back here for a second. One line worth looking at properly. That is t times here. 2 pi right here. 2 pi, 2 times pi, like the pi number, as in math. 2 pi times frequency times t, or t stands for time, of course. That t is the entire time axis, all 1,000 values, and multiplying it happens in one go. Then sine of the whole thing gives you the whole wave. No loop anywhere. That is the vectorization from earlier. It's doing the real work. Very simple, very effective, and scalable. And remember, scalability matters a lot, specifically in this field when you're dealing with millions of data points. Okay. Now let's plot everything. Fun part. There it is. You can see the oscillation. You can see it is scruff as we added noise. That scruffiness is not decoration. Real recordings look worse than this. Scalp EEG signals are on the order of tens of microvolts, which is very small. Well, very small voltage to pick up through skin and skull, and everything from your heartbeat to the mains wiring in the room is competing with it. Let's try to describe an array. NumPy carries the summary statistics around with it, the mean, the standard deviation, the minimum value, the maximum value. You just ask the array. This is very beautiful. This very much makes life easier and for us. So as I mentioned, you just ask the array and it answers to you. Note that mean is close to 0, which makes sense because a sine wave spends as much time. Right here you can actually observe it. A sine wave spends as much time above the 0 as much it spends below the 0. And look at the last line, because it is a 2-step move worth learning. Argmax. The whole logic is actually very much the same. You take your array dot the mean, and parentheses gives you the mean, dot std gives you the standard deviation, dot mean the minimum value, the max gives you the maximum value, dot argmax, but is actually very cool to know. It's very useful. And argmax does not give you the biggest value, like the maximum value. Then it gives you the position of the biggest value. Then you fit that position into the time axis, and now you know when the peak actually happened. Value and positions are different questions. Half of signal analysis is asking when, not how much, and argmax is how you ask. Okay, let's learn about slicing a time window. Basically selecting a time window. Last idea for today, and it is the one you will use the most. Let's say you only want the data between half a second and 1 second. Maybe that is your post-stimulus window. Maybe the participant moved before that and you are throwing the start away. You could count out the sample numbers by hand. Do not. Instead, write the condition. This window is also called a mask in signal analysis. Imagine it as a mask that you put on the face of your data. It says t greater than or equal to 0.5 and t less than 1. And what comes back is not the data, it's a list of truths and falses. One for every sample, saying whether that sample is in the window or not. Right here you can see. Then you hand the mask back to the signal or the window and you get exactly the samples where the answer was true. Like 250 samples in the window. This is called a Boolean masking. It is beautiful because you write the condition in the same words you say it, like exactly you can see it. Like for the time, t stands for time, larger than or equal to this time, and or t for less than this time, and it returns you a list that you can actually, as a mask, put on your data and see where it is actually true. So Boolean masking is beautiful. And give me the signal. So give me the signal where the time is between here and here, or give me the signal trials there where the response was correct, or basically all done using the same logic. Let's run the masked plot. This is very cool. Okay, let's see what do we have. The gray is everything. The blue is the window we selected. No counting, no off by one errors, no guessing. Which sample number half a second is. Okay, so today arrays instead of lists, whole array operations instead of loops, and a signal we are going to keep. There is an exercise at the bottom. Call the function with the noise level set to 2 instead of 0.5 and plot it. Then the 10 Hz oscillation is still in there mathematically, exactly as strong as before. You will not be able to see it at all. Sit with that for a second, because it is the honest situation with most real recordings. The thing you care about is in the file, and it is invisible. Session 8 is where we get it back out. Before that, session 6 is pandas, which handles the other half of your data. Not the signal, but everything around it. Which trial, which condition, which participant, how fast they respond. Signals and tables are the two halves of every experiment, and you need both. Notebooks and data are all freely available for you on the GitHub repository, and the link is in the comments section. See you in session 6.